Ancient prospectors rarely stumbled upon shining nuggets of perfect metal. Most civilizations spent centuries unearthing complicated, stubborn rocks that looked nothing like the tools they hoped to create. The core problem sits at the atomic level. The raw materials we need are tightly bound within complex, unyielding crystalline structures, held captive by strong chemical bonds. Let's focus on a single, valuable target element. We'll call it metal M. In its raw, natural state, metal M is effectively locked inside a microscopic cage. Specifically, metal M is typically found trapped within one of two chemical configurations: heavily interconnected carbonate ores or equally rigid sulfide ores. You cannot apply brute physical force to free it. Smashing the rock to dust or even melting it down in a furnace fails to separate metal M because those chemical bonds easily overpower sheer physical force. Acquiring a usable metal requires chemical liberation. To extract it, we must molecularly dismantle the rock to release the atoms trapped inside. This presents a major metallurgical roadblock. We cannot take those complex sulfide and carbonate ores and refine them directly into a pure metal. The chemistry simply won't permit it. To bypass those stubborn bonds, we rely on a required intermediate step: conversion via oxidation. By placing these specific ores into a highly controlled environment and blasting them with targeted heat and oxygen, we force the molecular structure to break down and completely rearrange itself. This heat strips away the complex carbonate and sulfide bonds, leaving metal M bonded exclusively to oxygen. This new oxide state acts as a necessary gateway. A direct metal-to-oxygen bond is much easier to snap in the final stages of purification than the sprawling, heavy lattices we started with. Mastering this intermediate oxide conversion simplifies the extraction. Reducing an oxide requires significantly less energy and fewer chemical steps than processing raw sulfides or carbonates. Once the oxide is reduced down to a base metal, a new problem emerges. The material is still riddled with microscopic impurities that severely compromise its strength and conductivity. To strip away these final flaws, we use a high-tech purification solution known as electrolytic refining. The foundation of this environment is a specialized liquid chemical bath, which we call the electrolyte. We lower our source material into this bath. This bulky, impure block of our newly reduced metal M acts as the anode. Opposite the anode, we place our target destination, the cathode. This is a pristine, incredibly thin strip of perfectly pure metal M. When we introduce an electric current, the anode physically begins to dissolve. Pure metal M ions detach, migrate straight across the liquid electrolyte, and fuse smoothly onto the cathode, leaving all the physical sludge and impurities behind at the bottom of the vat. Electrolytic refining operates as the ultimate precision filter. By directing electrical currents, we physically rebuild the metal, atom by atom, into its completely flawless state. Here we have the final state of metal M, entirely stripped of its natural bonds and completely purified on the cathode. The journey to get here was strict. We started with a locked ore, forced it into an intermediate oxide, and electrified it into perfection. This resulting purity is entirely unnatural. You cannot find a metal this clean in a riverbed or a mountainside. It exists solely through deliberate human chemical intervention. And this heavily refined state is mandatory for our daily lives. The structural stability to build towering infrastructure and the perfect conductivity required to run the global power grid rely completely on this precise level of purification. Technological progress relies on mastering these elemental transformations. We take dense, unyielding rocks and chemically reconstruct them into the foundations of human civilization.